The notes for Unit 7, Lesson 1 will cover ionic, polar, and nonpolar molecules. A lot of the information from this lesson will be a review, and we're actually going to take this lesson and split it over the course of 2 days. So today we'll talk about polar and nonpolar. Tomorrow we'll follow up with more ionic and covalent. So Unit 7 covers solutions. So we'll be talking about why certain substances will dissolve in other substances or not, and we'll also talk about the strength and concentration of different solutions. So for Unit 7, we'll cover all this information again in about the next 2 weeks. So make sure you have your notes packet available. The information in your textbook from Unit 7 will cover chapters 15 and 16 if you need some supplemental material. You will also need your yellow periodic table packet because some of the review goes back to looking at the actual periodic table to classify different substances. All right, here we go. So polar and nonpolar. Polar and nonpolar we probably talked about in first trimester. So this will be a review, but it's been a long time. So polar, if you have a polar molecule, that means that one side of the molecule has a partially positive charge, the other side has a partially negative charge. And the difference in charges is caused by a difference in electronegativity values. So electronegativity is basically the tendency for an atom to attract an electron. So if it has a high electronegativity value, it's going to be the atom or that side of the molecule is going to be more negative. If it has a smaller electronegativity value, that atom or side of the molecule is more likely to be partially positive. So each atom is assigned its own specific electronegativity value. You actually have a chart in your yellow packet of electronegativities. We're not going to go into as much detail for this unit. We're just going to look at the overall shape of the molecule to determine whether it's polar or nonpolar. So, with the term partial, so this symbol here, which is like kind of the mix of an 8 and an S, is the symbol for partial. So this side of the molecule would be partially negative because if you look and compare the electronegativities, oxygen has a higher electronegativity value than hydrogen. And so hydrogen would be more positive, oxygen would be more negative. So when you have a polar molecule, that molecule has surface tension. So surface tension is the inward force or pull to minimize the surface area of a liquid. So if you take wax paper or sometimes even like, the water on your car will bead up. So when the water beads up on the surface, that's surface tension, or that's due to surface tension. So because water has a partially positive and partially negative side of the molecule, those forces attract each other and kind of pull that molecule inward. So polar molecules in general will usually have the property of surface tension. Nonpolar molecules means that the molecule does not have an overall charge. So if you look at the shape of CO2, how it's drawn here, think about it as a tug of war. So oxygen is pulling to the left with a specific strength. The other oxygen is pulling to the right with a specific strength. Because both sides are oxygen, that means that they're pulling equally. So basically, if you're playing tug of war with someone exactly the same size and strength as you, the rope is not going to go anywhere. So because the rope is not going to go anywhere, there's no overall charge. So those pulls from the oxygen molecules will cancel each other out. And so this would be nonpolar overall. All right, so if you have these pictures, the first one is water. So if you look at a water molecule, this is what the Lewis structure would look like. So again, we're not going to, you will not be asked to draw the Lewis structure. That was a long time ago that we did that. And so you'll have to look at the pictures of the molecules to figure out if it's polar or nonpolar. So if you look at water, water has these lone electrons on top of the molecule. So these lone electrons are not bonded to anything. So here you have bonded electrons, but then here you have these unbonded electrons, and all of those electrons repel each other. And so because this side of the molecule is different than the other side of the molecule, that means that the molecule is being pulled differently. So these electrons are going to pull differently than these electrons. So because there is a difference in pull, that molecule is going to be polar. If we look at O2, oxygen would be pulling tug of war to the left with specific strength, and it would be pulling to the right with the same strength. So that tug of war is going to cancel each other out, making O2 a nonpolar molecule. CF4, you have these fluorine atoms pulling on each side of the carbon atom. Since they're all fluorine atoms, they would all be pulling with equal strength. So that tug of war is going to cancel each other out, meaning that the molecule is nonpolar overall. So you kind of just look at the general shape and look for symmetry. So if the molecule is symmetrical, then it's going to be nonpolar. If there's any difference in the electrons, that molecule will be polar. All right, so let's try a few more. So take a second, pause the video, try these on your own. Take a guess, take a risk. Even if you're wrong, it's okay. And then come back and we'll check our answers. All right, so SO3, you have oxygen pulling equally on each side of the sulfur. Remember, when you're talking about it pulling equally, you're talking about what element is bonded to the central atom. So because all three elements are oxygen, those all have the same strength because they're all oxygen. So these would be pulling equally. Sulfur does not have any lone electrons around it, so this molecule would be nonpolar. This one is tricky because it does have these double bonds, which is different, but the strength of the pull is going to be determined from the actual element itself and not the number of bonds. All right, NH3, you have hydrogen pulling on this end, hydrogen pulling up, hydrogen pulling to the right, but then you have these lone electrons down here that are different than any bonded electrons. So those lone electrons make it different, which means that this molecule is going to be polar because one side is pulling differently than the other. All right, so here are a few more terms when we're talking about substances dissolving into one another. Aqueous solution. So a solution is when water contains dissolved substances. So a solution means that all of those particles are going to dissolve in water. And in a solution, you have two parts to a solution. You have the solute and you have the solvent. So the solute is the substance being dissolved. So I always say it's what you put in. Oops. And then the solvent is the substance doing the dissolving. So if you have a saltwater solution, salt is what you put in, so that would be the solute. And then water would be the solvent, and water is doing the dissolving. All right, so the process of solvation. Solvation is when a substance dissolves into another substance. So this also is a review probably from trimester 1. The properties of how a substance will dissolve into a solution depends on whether it's ionic or covalent. So ionic substances are made up of a metal and a nonmetal. So if you remember, when you look at the periodic table, I'm going to draw a very rough sketch. You have this zigzag line that goes down the right-hand side of the periodic table. Everything to the left is a metal, and everything to the right is a nonmetal. So when you find these elements on the periodic table, if you have a metal, that would be any of these elements to the left of the zigzag line. The only exception is hydrogen. And then the nonmetals are going to be everything to the right of that zigzag line and hydrogen. So if you have a metal and a nonmetal combination, that is going to be ionic. So Na is a metal, Cl is a nonmetal, so that combination would be an ionic substance. And then covalent is two or more nonmetals, so C2H4O2, carbon, hydrogen, and oxygen are all nonmetals, so that would be covalent. So when you have an ionic substance that dissolves, ionic is going to break apart into positive and negative ions. And so when you have salt and you put it in water, salt is going to break up into all these positive and negative particles. So ionic will break apart into ions, which are charged particles. So ions, again, have a charge, so the positive and the negative. Covalent substances, if you notice, this molecule of sugar looks exactly like the molecule of sugar when it's dissolved into water. So covalent substances do not break apart. They stay together as a whole molecule. So they do not have the charged particles. They just stay together as a molecule. So that's the difference of ionic and covalent when substances dissolve. So make sure that you, in your notes, clarify whether the substance is ionic or covalent, and include the pictures. All right, so this will explain the phrase likes, dissolve, likes, and then we'll go ahead and on the next slide show you the wording for the key concept. So likes, dissolve, likes means that like substances are going to dissolve in one another. So salt, we know, is ionic, and because we know it's ionic, we know it's going to have positive and negative particles. Water, we know, is polar, which means it has those partially positive and partially negative particles. So because you have positive and negative particles from ionic, and you have partially positive and partially negative from your polar substance, those two will dissolve into one another. Over on the right with oil and water, we know oil and water do not dissolve in each other. We know water is polar, so oil must be nonpolar, which means that oil does not have those charged particles. So polar and nonpolar will not dissolve in each other. So here's the key concept that you'll write down with likes, dissolve, likes. So substances that dissolve most readily in water, so remember water is polar, will include ionic, because ionic has those positive and negative charges, and polar, because polar has a partially positive and partially negative charge. So polar substances will dissolve in polar substances. Ionic substances will also dissolve in polar substances. So if we look at the list on the bottom, so CO2, I'll draw these out so you can see the picture. So CO2, if you think of this molecule playing tug of war, those molecules, or the poles, are going to cancel each other out, so that is going to be nonpolar. CCl4 is going to look like this. So again, all of those sides are pulling equally, so that is also going to be nonpolar. So CO2 and CCl4 will not dissolve in water because water is polar. and they are nonpolar. Na2SO4 has a metal and a polyatomic ion, so that is going to be ionic, which means Na2SO4 will dissolve in water. PCl3 will look like this. So because PCl3 has these extra electrons, that makes it different on one side. So the molecule is going to be polar, which means that that would dissolve in water. MgCl2 is ionic because of a metal and a nonmetal, so that means that will dissolve in water. BaCO3 is also ionic, which means that will also dissolve in water. I2 is going to look like this. So if you think about this molecule playing tug of war, one side is pulling the same as the other side. So this is going to be nonpolar, which means it will not dissolve in water. So we'll do some more practice with all of these. I know it's a lot of information. So that is actually the end of lesson 1, part 1 notes. We'll do the second part of lesson 1 tomorrow.